So this one's a domain and range, which is mentioned briefly in 9.6, and it has a couple examples, and I thought it'd be good to kind of do a whole session on it because a lot of people struggle with this, and in college algebra we talk more about domain and range, so I thought it was worth doing an hour and going through many different examples so you can really pin down the idea and what it means. So we first need to start with the term relation, because the definition of domain and range is in terms of relation. So you need to, backtrack here. So a relation is just a set of ordered pairs. That's it. The word relation basically means that there's some relationship between the input and the output. The two numbers are related in some way. Usually input, output. And so we do talk about functions. You'll learn about functions this week. Relations don't have to be functions. It just means that there's some relationship, no matter what it is. So our x is always our input or our independent variable, and y is the output, the dependent variable. That's what I talked about when I had my graphing last week. And so if there's any kind of relationship between things, that's called a relation. And you could have a table that forms a relation, a set of ordered pairs can form a relation, a graph can form a relation, an equation can form a relation. There's any way to demonstrate that you have a relation going on. It's just you're showing that there's some relationship between the two things. And so that's when we talk about domain and range, it's in terms of relations. Basically, anything that has a relationship, there is a domain and a range. So the domain is the set of input values, or it's a set of allowed input values. So if you have a specific list of numbers, like if you've got a sort of set of ordered pairs or a table of values, your domain is just listing all of those x values. If you have an equation or a graph, with an equation, there's no list of x values. You're basically looking at, well, what numbers can I plug into this equation and get an output for? So it's the set of allowed input values, numbers you can plug in. And for most equations, there's an infinite number of things you can plug in. So your domain is all real numbers. When you're looking at a graph, you're looking at, okay, our x is our input, and so that's looking at the horizontal axis, and you're looking at where is my graph, like for what x values do I have a picture, is my graph going, so you're looking at it graphically and saying where does my graph exist as far as looking at the x. So that's domain. When it's ordered pairs or a table, you're just listing things. When it's an equation or a graph, we can't list every single possible number, so that's where we usually use interval notation, which we learned about in the section about inequalities. So it depends on what you're looking at, how you write your domain and range.
Okay.
Now range is just like that, but it's the y values. So your range would be just listing all of the y values for your ordered pairs, or in a table what your y values are. When you have an equation, it's the possible y values or the possible outputs, but it depends on what the input is. So you're only considering, well, depending on what I'm allowed to plug in, what would my output be? What would be the outcome? So those would be, that's your range. And you can't always have every number on the output. Like maybe you can plug in any number you want, but based off of the equation or the graph, you're not going to get every number back out. So you might have your range might be smaller. And it's same thing with a graph. You're just looking at, okay, what y values do I actually are covered on my graph? When you look at it that way, you're like, where does this exist in terms of your y or your vertical axis? So range depends on the domain, because you can't determine the range until you know what the domain is, because it depends on your inputs that you're plugging in.
Yeah.
So we usually find domain first, and then we find range. And where domain and range are helpful, it's helpful because it tells you if you're going to make a table or make a graph, you want to make sure you know what numbers you're allowed to plug into the equation, because if you plug in a number that will make you divide by 0, that's not going to be helpful for graphing, because we can't divide by 0. So understanding domain helps you pick your numbers to plug into a graph. And then domain and range is also helpful in real world situations, because then you know, well, does it make sense to have these values as my input? Like if my input value is time, does it make sense to plug in negative numbers? No. There's no negative time, you know? Or your range, it's the same thing as like, well, what would be the outputs? If I'm doing stock prices, is it possible to have negative stock prices? No. So, you know, I won't have negative numbers in my range. I'll only be looking at positive numbers. And that helps you when you're graphing, because it helps you focus. Well, if I'm going to graph this real world situation, if I'm not going to have any negative numbers, I don't even need to have that part of the graph. So it allows you to kind of focus over where you want to have your graph. Where is your important parts that you're looking at in order to graph? Okay. And so that's where domain and range is important. So I'm just going to go through tons of examples. We're going to start with ordered pairs and different types of relations, and then we'll go into graphs and then equations. So we're just going to kind of go through all different types of things.
All right, I'll just hang on.
Yep. So here we got two examples. These are relations because they're basically a set of ordered pairs. So they're sets because they have the curly braces, and then they're ordered pairs inside there. And ordered pairs are always x comma y, and our domain is always the x, and the range is always the y. So when we write our domain, we're basically writing down all of the x values, and we write it as a set when you have ordered pairs. So we're going to have our set notation. So you have the curly brace, and then you write down the x values. So the first ordered pair, I have -3. Second one, I have -2. Third one, I have 1. And then the fourth one, I also have 1, but if it's already written down, you don't have to do it a second time.
Oh, okay, gotcha.
So if it's already down, you don't need to do it again. So it kind of saves you some time.
Yeah.
And then the range is just the y values. So again, I'm going to have my little curly brace. And the more you go through math, the better you'll get at drawing these curly braces. When I first did them, like when I was first, I just did like a little squiggle, and I figured, okay, that's close enough. And it's basically, if you ever made like little seagulls, like, you know, when you're just doodling, it's like a sideways seagull. So
I recall you talking about that last night. Yeah.
Yeah. So I've got my y value. The first order pair is -1, and then the next one is 6. Then I have 3, and then I have -2.
Yeah.
Now you don't have to write the numbers in order from like smallest to largest. You can, but it's not a requirement. So I just like to write them in the order that I see them, because then I don't have to worry about doing any rearranging. So second one here. So again, we've got a set of ordered pairs, and so we just look at the first numbers for our domain. So we've got 9, 4, and -1/3. And then our range, they all have the same y value. So you only have one number written down in the set notation.
Oh, yeah, that makes sense.
Yeah. So instead of writing it 3 times, the only output there is 6. It's just one number that is the output.
I was ready for more, so have this big wide.
Yeah, don't need all that space. Now, relations don't have to be with numbers. And actually, when we talk about functions, you can have functions even if they're not dealing with numbers. As long as there's an input-output relationship, it's a relation. And functions specifically there's only one possible output. So here's an example. We don't have numbers, but we can still find domain and range. It's just now we're going to be writing words. So our domain is the set of the inputs, and the inputs are on the left, and the arrow is going to the output. So you can see that basically where the arrow is going, that's your output value. So our input is going to be these cities. So we've got Houston, Dallas, and San Antonio. And then the range is Texas, but because it's specifically written TX, you want to make sure that you use the right symbol. You use exactly what you see. So you don't want to write the word Texas, even though that stands for Texas, because it's not technically the same thing.
So you have to be extremely detailed in that situation.
Yes. Yeah. I mean, it's even when we have variables, you have to make sure you use the same capitalization. You can't change from lowercase to uppercase in the same problem. Like all of that really matters.
Okay. All right.
So yeah, so because it's TX, you have to use TX for Texas. But you can see that our relationship here is that our input are cities and the output is the state they're in. And so they're all in Texas. So you can see that there is a relationship between those.
Yep.
So here's another one. And actually on the left, our inputs are states. And then on the right, we have cities in those states.
Oh, okay.
So it's the other way around, but they still form a relationship. So our domain is New York and California. Now there are more than one state, but we're looking at just the ones that are part of our relation. And so those are the only two that are listed. And then for the range, we have 3 cities: Albany, Los Angeles, and Buffalo.
I'm glad you told me about that, because I would have easily, like with New York City, I would have put NYU.
Yes. Yeah. And if you put that, you're going to get it marked wrong because it doesn't match. It has to be exactly as it is.
I'm glad you instructed me on that. Thank you.
Yeah. Now, when you have like ordered pairs or a picture like this where it's very clear what the input and the output are, and it's the same thing if we had a table of values, you can put this in a table form. Finding domain and range is simple. You don't even really need to think. You just need to write down what you see. And you just have to remember which one is X and which one is Y. And if it helps, alphabetical order. X and Y are in alphabetical order. Domain and range are in alphabetical order.
Oh, well, gotcha. Good.
So, yeah, so if you think about it, if you put them in alphabetical order, that will help you. That will line it up. Now, you do have to start doing some thinking when you start getting graphs.
Okay.
Yeah, because it's like, oh no, now I need to actually see what's going on here. So here we have a graph, and it's a set of ordered pairs. So what helps some people is to translate the graph into ordered pairs or into a table, and then do the domain and range from there.
Oh, okay.
So we can do that. And so I'm going to just work on the left point. Our X value is at -5 and the Y value is at 4. And then I'm going to move over. My next one is here. So that's at -1, and then the Y is at -2. Then I have 0, 4. Keep moving to the right. I've got 3, 4, and then I have 5, -2. So I've just basically moved left to right and wrote the ordered pair for each of those points, and then put it in a table so that I can figure out my domain and range.
That's a good idea. Very organized.
Yeah. So then from the domain, it's a set of points. So I have my curly brace, and then I just write down all of my X values. So -5, -1, 0, 3, and 5.
And no duplicates. Nope.
There's no duplicates there. Yeah.
Yeah.
There are duplicates on the Y though, which is the range. Okay. So I have 4 and -2. And those are the only 2 Y values that we have.
Oh, see there? Oh, man.
Yeah, if you write something more than once and then you put it in, it's going to be marked wrong. So you want to double check that you don't have numbers written more than once.
Well, I put the 4 in as a negative. So
that would also be a problem. Yeah.
My glasses are in back order again. They went to a different lab because they tried 3 times and couldn't get them right.
Oh no.
So I still had to wait for my
I
glasses.
didn't think it was that hard to make glasses. I mean, that should be good.
I know.
When I had
Dang.
to get a crown, they kept messing that up. But that I understand because they have to like fit it just right, you know?
But that would still be just as frustrating because you have to keep going
Yeah.
back or you have to wait.
Yep. Yeah. And it's like, nope, it doesn't fit. Let's go back. Let's remake it again.
Oh my gosh, that would be a drag because I just got a crown put on. That would have been a drag to have to do that. Okay.
So an alternative to doing domain and range by making a table like this is to actually kind of look at your points and then kind of draw lines down to where they are on the x-axis for the domain and then read those numbers off of the x.
Oh, because I think that's a great idea.
Yeah, and then you can do the same thing for the y. If you draw them to the y-axis and then make dots, you can see that there's two numbers on the y.
Yeah.
And so you can do it that way as well to determine your domain and range. And usually I will do this visually. I won't actually draw these points or whatever, but I'll look at it and that's how I do it. I don't make a table, but the table's really good when you're getting yourself organized.
Oh, yes. Yep. So, okay, so you're showing us domain and range when we look at facts in front of us, but isn't there much more than this about I mean, I guess.
Well, the word problems you'll see.
You're holding on me here.
Yes, when we get to word problems and equations, because then it's not in front of you, and then you have to do more thinking.
Oh, okay. Okay.
So here we have a graph, and this is not a series of ordered pairs. So this would be an example where you don't want to make a table because you can't write down like all of the possible points where it connects.
That's true.
So this is where using the method that I showed where I'm kind of drawing it down to the x and y axis, that's where I would use that method. So I would do the x first, and so I just kind of look and I'm like, okay, between where are my x values on the graph? You can see that I'm kind of graphed about like -2.5 to 2.5.
Yep.
Now, when you have arrows on your graph, that implies that it keeps going. And so because we have arrows there, that's telling us we're going to keep going to the left, and then we're going to keep going to the right.
Okay.
So for my domain, you can think of it as we've got this number line covered. And so this is where the interval notation comes in that we talk about in 2.8 with the inequalities. So we're graphing from -infinity to infinity, and basically my whole graph is covered here. Let me change to a different color because like the way that I have it graphed, the whole number line is covered. So
that way.
When your whole number line is covered, or when your whole x-axis is covered, that is all real numbers for a domain.
Okay, all real numbers.
And we usually write that in interval notation as -infinity to +infinity.
Okay.
Because you can read that off of your number line. Your left goes to negative, your right goes to the positive. So for the range, we do something similar, but we look at the y values. So you're looking at now the horizontal axis, and so you're kind of graphing, okay, where do I have it? Where does my graph exist? And so I draw on my vertical axis where I have y values, where my graph actually is. And then the arrows are on the top part, so that's where my arrow is going to be on my y-axis.
Okay.
So if we think about it again as a number line, but now our number line is for y. So the lowest number that I have is at -2. So you can see that that's where the lowest point is. So if I have -2 on my number line, and then we're shading up, which is going towards more positive numbers. So if I turn that into a number line graph, I've got my arrow going to the right, and 2 is part of the graph, so that's our solid dot or a bracket to indicate that point is included. So I'm taking my picture and what I see, I'm translating it to the y-axis, and then I'm rotating the y-axis so I can get as a number line, which allows me to write my interval notation.
Okay.
And so then from the interval notation, you just read it from left to right. So at the left part of my shading, I have a bracket at -2. And then I'm going all the way to the right where infinity is, and infinity always has a parenthesis.
Because the arrow keeps going and we don't know where it stops.
Exactly. Okay. Yeah. And another way to look at this is if we wrote it as an inequality, basically our range, it's not x, it's y values are greater than or equal to -2. So you can also think about it as an inequality. The normal domain and range, we always write them in interval notation with the brackets, the parentheses, that sort of thing. But if it helps, and you can kind of look at it graphically, you're like, okay, all of my y values are greater than or equal to -2.
Okay, yeah. So that has to be, that's why the bracket, greater or
the equal to, yep. So graphing is usually where people struggle with domain and range because it takes time to kind of be able to translate what you see into the proper interval notation.
Yeah.
And so I recommend doing it this way until you get good at it. You know, if you have to take a lot of math, eventually you're going to want to get to the point where you can just look at the graph and you can read it and you don't have to do all of this, and you could just say, oh yeah, I know what the domain is, or I know what the range is. And when you get to college algebra, you'll learn about different types of graphs and learn that like certain types, their domain is always all real numbers, or the range will always be this. And so if you know what type of graph it is, that can also, you can just memorize what your domain and range are.
Very interesting. Okay.
So here's another one with a graph. So we'll do first our domain. I probably shouldn't do that in blue since our graph is in blue. So I'll go back to the orange. So our domain is the X. And so wherever I have my graph, it's basically, it's everywhere here, but we don't have any arrows. So it's not going on to infinity.
It's just between -5 and 5.
Exactly. So if I draw my number line, I've got -5 and I have 5. And then I'm only between those numbers. And then because I'm including the endpoints, because we do have points at 5 and -5, those are going to be brackets, and then they always face towards where you're shading.
Mm-hmm. So then the ordered pair for the domain would be bracket -5 x, no, yeah, x, no. So then it would be equal to or less than -5.
So we could do it, you're kind of combining both of these. No. So as an inequality, we'd write it as -5 less than or equal to x less than or equal to 5. In interval notation, it would just be -5, 5 with brackets on either side.
Okay, and when we write the lower one, the lower equation you wrote, not equation, it's not equation, expression.
Yeah, normally that would be written something like this.
Okay, all right, yeah. That's what I'm looking for.
Yeah, that's the set builder notation. But
okay,
you're going to want to do it as the one with the brackets because, well, it's easier. You don't have to write as much, you know, for one thing. And that's what is traditional for when we're writing domain and range.
All right.
And so I'll get my range set up. So for the range, the y values you can see that our y values are basically between -2 and 2.
Y values -2.
So we don't have anything bigger than or smaller than that. So that's going to look very similar. We just have different endpoints here. And so our range is going to be from -2 to 2.
Okay. Brackets.
And what this means in terms of, like, if we had an equation for what we're looking at right here, and what we're looking at, the graph is of an ellipse, which is something that you learn how to write equations for ellipses when you take pre-calculus. But what this domain and range means is that when you have this equation of an ellipse, if you plug in, like, say 10 into your equation, you're not going to get a y value out. It's going to cause you a problem. There will be no solution. I think what happens is you end up with an imaginary number, which is something that we talk about in college algebra. So you get something that you can't graph.
Mm-hmm. Okay.
So it's outside of your domain because you can't find an answer. You solve it. It's not something you can put on a graph. And so then what this means is that if I plug in any number between -5 and 5, my y values are only going to be between -2 and 2. So that if I get a y value that's outside of that, like if I got a y value of 8, I made a mistake because that's not in the range. That means you made a calculation mistake because it can't be outside there.
It's not on the graph, and there's no error.
It's not on the graph, exactly. So that's another reason why domain and range can be helpful, because if you have an understanding of what output values you're allowed to have, that tells you if you get something that, is allowed. Because if you don't, you made a mistake somewhere. So it just kind of adds to your ability to understand what you're doing, and it's another way to check what you're doing. Mm-hmm. And you can always put your equation into a graphing calculator to get a graph to determine what you're doing in range R to get an idea of whether your stuff's allowed. So now we're going to move to equations and word problems where domain and range are helpful.
We're working up to it slowly.
We're working, yes. So an electrician charges $75 to visit, diagnose, and give an estimate for repairing a refrigerator. If Helena decides to have her refrigerator fixed, she will then be charged an additional $50 per hour for labor costs. The equation for the total cost, C of X, so that's function notation there, of fixing the refrigerator can be modeled by the linear function C of X equals 75 plus 50X, where X is the number of hours it takes the electrician to fix the refrigerator. So it's telling us our input is the number of hours, and then our output is the total cost. And so this is a linear equation, and a lot of things are linear equations where you have things that are like per hour. We know the total cost, it's a flat 75 that you have to pay, so we've got that 75, and then we're adding on the additional $50 per hour, and so that's the 50x. So when you look at it, that equation makes sense for what we've got here. Yeah. So determine the domain and range. So we have two different ways that we can consider domain and range. We can consider domain and range of the equation itself, and we can consider the domain and range of the situation. Because if you look at just the equation and you ignore the real world aspect of it, you get a different answer than when you consider, well, in reality, what numbers are we going to have here? So we're going to look at this from two perspectives. So we're going to look at it in terms of the equation first. C of X equals 75 plus 50X. So linear equations, we've just learned about lines last week. And there is no X value that you cannot plug into one of these. And if you look at your graph, there's arrows on both ends. So our domain for lines is all real numbers, and it's always going to be an all real number if it's a linear equation.
Okay. Numbers.
So that's one of those that if you're like, oh, I have a line, my domain is going to be all real numbers, which we use negative infinity to positive infinity. And that just means I can plug in any x value I want, and I don't have to worry that it's going to cause me problems.
Aha. Okay.
Now for lines, the range is also all real numbers. It's possible to get any possible output that you want when you have a line. So the domain and range are exactly the same for lines. You can plug in any number you want, and you can get any number as an output. So when you look at it as an equation, and you can graph it and look at it that way, you can draw your graph like we did, draw the lines, look at the arrows, and you'll get the same thing. This is one reason why we teach linear equations first, because then you don't have to worry about, well, can I plug this number in? Is it going to cause me problems? You know, it won't. You can plug in anything you want. So the equation has all real numbers, but in real life, for this situation, it's not going to be all real numbers. So, and let's see, how do I want to write this? Whoops. Let's just write in context. So just in context of the situation here. So our domain, our x values are the number of hours that the electrician can do to fix the refrigerator. Well, the electrician can't do negative hours. So it doesn't make sense to have negative values. It's possible the electrician puts in 0 hours because maybe he can't fix it. So if we think about the possible number of hours that the electrician could do, it'd be 0 or higher, basically.
Right. Mm-hmm.
So our domain would be x greater than or equal to 0, or in interval notation, it's a bracket at 0, and then it goes to infinity. Now, we're unlikely to take infinite number of hours, but it's hard to estimate what the actual stopping point would be for the number of hours. Mm-hmm. So we can easily say, oh, for bare minimum 0 hours, but it could be 5, could be 8. I mean, I don't know how many hours it might take until there's no more possible. So we'll just use infinity there because we can't put another cap on it. So you can see how that differs from the actual equation, because the equation says I can plug in anything you want, but in context of the problem, that doesn't make sense. It narrows your domain down.
So the range, okay, I was gonna say, so
yeah.
The range.
So when you're doing the range like this, again, we're not going to have an infinite amount of cost. So then you have to look at it in terms of, okay, let's look at my endpoints. If it takes 0 hours to fix the refrigerator, what is the minimum payment? What is the minimum cost of this?
Oh yeah, $50.
75, because that's a flat rate.
I'm sorry, I was thinking of the actual hours. And
yes, right, the actual hours, yes. Yeah. But it's 75. You put in 0 for x, you're going to get 75. Okay, yeah. So our minimum cost is going to be 75, so that we know our y value has to be greater than or equal to 75.
Aha. Okay.
Now, again, we don't actually have an endpoint for plugging numbers in. We don't have a maximum number of hours, so we can't really determine a maximum cost either. So all we can say is that the range is 75 to infinity.
But we hope not infinity.
Mm-hmm. We certainly hope not infinity. There will be, for a specific person that might say, well, I'm only willing to pay this much money.
Right. That's me.
And then if you're like, oh, if they're only willing to pay, like if I'm only willing to pay $2,000, you could work backwards, plug that into your equation and solve for the number of hours. and do it that way. So if you have a range that you're willing to pay, you can work backwards to find the domain as long as you have an equation.
Great.
So here's another one, and this is actually my last word problem because there weren't too many in the section. For people 16 years old and older, the maximum recommended heart rate, M of X, in beats per minute is a function of a person's age X in years. So they give us the equation, 220 minus X. So as looking at this graph or the equation, as you plug in higher numbers for X, that number is going to go down because we're subtracting X. And then they tell us specifically for X greater than or equal to 16. This is the domain that they're giving us. So in this case, they're specifically telling us the domain. So if they give you an inequality for X, that is the domain. So it's X greater than or equal to 16. And when you translate this to interval notation, that's going to be a bracket at 16 and then to infinity.
Yeah.
Now, there actually is, if you look at it further, they don't give us an end point for the age, but we can think about there is going to be an end point because humans don't really live. I think the maximum is 120 that somebody's lived, maybe older, but it's like most people don't live that long, so 120. Right. And if you look at the equation, we know that heart rate has to be positive. You can't have negative heart rates.
No, you can't.
So if you look at the equation, we know that our 220 minus X needs to be greater than or equal to 0. You can solve that to kind of give yourself a maximum. So if I subtract 220 from both sides, oops. And this is why we learned how to solve inequalities. That gives me negative X greater than negative 220. And then if I divide both sides by -1, that reverses the inequality. So now it's a less than or equal to. So we divided by a negative.
Oh, yes. Okay.
And I get X is less than or equal to 220. So since we know that heart rate can't be negative, we basically worked backwards by creating an inequality there. And this tells us, well, X has to be less than or equal to 220. So we could modify our domain and say, well, 220 is the other endpoint, because otherwise it doesn't make sense anymore.
That's true. And it became a bracket.
It became a bracket because it's included. We can be equal to 220. Okay. And then you'll get 0 for your heart rate, which if you're that old, you're probably dead anyway. So now the thing about domain and range is that even if you have an equation, sometimes if you go too far out from what makes sense, the equation doesn't make sense anymore. Like if I have somebody who's 200 years old, well, some people, let's say somebody could live to 200 years old. If I put that in the equation, their heart rate's going to be 20. There is probably some point where your heart rate kind of flat, like that the maximum doesn't go much lower. So there probably is some point where it's like, no, your maximum heart rate is, maybe 70 at some point, and it doesn't go lower than that. According to our equation, it kind of goes on forever. So there's some point where the equation breaks down. And so when you think about domain, you want to kind of think about, well, where does the equation make sense? Now, I don't know where that equation stops making sense, so this is the best guess we can come up with because I'm not a medical professional. I don't know, the maximum recommended heart rate for some, where that maximum is going to stop before it starts becoming unhealthy. Where is your heart rate too slow, basically? I don't know. But this is the best we can come up with. But you do need to think about it when you have real world situations, is that even if this is the best we come up with mathematically, there may be other factors that at a point where the equation doesn't hold anymore.
Right, right.
But
good point.
We don't know, so we just have to go with what we have.
Right. Right.
So then when we do the range here, so your range is based off of those, the domain that we plug in. So the lowest point for domain is 16. So if I plug that into the equation, 220 minus 16, that gives me 204. And then we know if we plug 220 into the equation, that gives us 0. So this basically tells us that our range is between 0 and 204. So you kind of use the domain endpoints to determine what the range is when you have an equation like this. If it wasn't linear, it's a little harder to do, but when you have something that's linear like this, you just basically need to figure out where your endpoints are. And then that tells you what your range is. And that's why I say that range is based off of your allowed inputs, because we had to use the inputs to determine what the outputs would be. So when we write the range, we have to go in order from smallest to largest. So 0 is the smallest, so that's going to be on the left. And then 204 is the largest, so that's going to be on the right. So they're not like ordered pairs because the 0 didn't go with the 16. 204 was the output from 16, but we write them from smallest to largest, and so we write it 0 to 204. And again, there's probably some minimum there that's not 0 that makes more sense, but I don't know what that is.
Okay.
So that's domain and range, and because there's so much interpretation on something like this, the problems that you get for domain and range in the like in Connect Math, it won't ask you for a range in like a situation like this. It'll be like, what's the domain? And it'll be like, well, what did it give you? It gave you x greater than or equal to 16. So it tries not to be too tricky, because you could think about these in many different ways based off of the information that you have, how much you know. So domain and range can be pretty wishy-washy in real-world situations. So don't overthink it when you're doing the homework. Go with, well, what's the most obvious based off of what they're telling me.
Okay.
And so if we did have, for this particular problem, if we said our domain was 16 to infinity, then our range would probably be negative infinity to 204 instead of 0, because we wouldn't have that 220 ending point, and so it would just keep going lower and lower and lower as we plug in higher x values.
Interesting. Okay.
Yeah, of course, doesn't make sense.
I know.
But, that's where you have to get some common sense in here, and you have to, say, okay, these are the assumptions that I'm going to make. I'm assuming that having a heartbeat below 0 doesn't make sense,